Good morning. Welcome to this third invited talk of the conference. It's a great pleasure for me to introduce ZicoKolter. Zico got his undergraduate degree from Georgetown University and then his PhD degree from Stanford. He went to MIT for a postdoc for 2 years and he's now a professor at CMU in computer science with affiliated positions in robotics and electrical engineering. His areas of specialties are machine learning and optimization, and in recent years he has been working a lot on smart grids and applications of optimization, control, and machine learning in those fields. So I'm really looking forward to hear what he has to say today. So Zico, welcome. And
thanks so much, Pascal. It's great to be here. I think I only know a handful of people here, so if I don't know you, please come up and introduce yourself. I would love to chat more about this or about any topics. Fortunately, the topic of my the title is a very broad topic. It covers a set of all possible things that I could talk about research-wise. So I'm not going to be off topic certainly, but I'll hopefully talk about things that are of some interest to this community. Let me start off by talking a little bit about sustainable energy. And I imagine actually Carla on Tuesday, I think it was, may have covered some similar themes. This is an excellent quote defining what sustainable means. It means it's essentially development that meets our present needs without sacrificing the needs of future generations. And I think it's fairly well established right now that at least our consumption of energy across the world is not particularly sustainable. So if you look at where, for example, this is a chart from the US, if you look at where most of our energy comes from, it's fossil fuels. About 87% come from fossil fuels, which raise many concerns about the ultimate long-term future of these things. These are ultimately finite resources, but the most pressing concern probably is about the effect these are having on the environment. They are increasing the carbon levels in the atmosphere, and this is causing at least some degree of concern amongst many people. And in fact, this now shows the carbon dioxide concentrations in the atmosphere over the past 1,000 years or so. And in fact, we are, if you look even further back, this recent period looks like a straight line going up. We're really sort of in unprecedented times in terms of our level of increase. Now, in response to this, a lot of governments across the world, with the US maybe lagging behind in some sense, but hopefully all starting to band together a little bit more, we're trying to make some fairly radical adjustments into how we generate power and how we use energy. And this will bring me from talking about energy broadly to talking about electricity in particular, because things that we're doing, like transitioning to renewable energy sources, have the biggest effect in some sense on electricity. And so this will bring me to this notion of the electrical grid and the smart grid. The common saying about the electrical grid is that if Alexander Graham Bell came forward in time, he was the inventor of the telephone. If he came forward in time to our present state, he would not understand at all our current infrastructure. He could learn about it. He's a smart guy, I'm sure. But he wouldn't understand it right away. Whereas if Edison or Tesla or Westinghouse came, they would sort of say, yep, that makes sense. It's about what we expected. Because the grid has not really changed in over 100 years, approximately. The same paradigms exist where you have centralized generation, at least ignoring this one for a second. You have transmission and distribution, actually separated into two things, that transport the energy from the generators to the end users, which include largely residential, commercial, and industrial consumers. And as I said, this infrastructure here has not really changed for about 100 years. But I would argue that that is all going to change fairly soon. And the reason is because of the rise of these renewables. So the installed capacity of wind is still growing very rapidly. This shows just plots from just 2000, how much there's been an increase in installed wind capacity in the last 15 years. A similar chart holds for solar, a little bit lower right now, but certainly likely to catch up at some point. And this is not a minor detail here, because these resources, the renewable resources, are non-dispatchable. In other words, we can't turn them on and off. We can't control them like we can control traditional generation. And so there are fundamentally different challenges that arise when you have all these resources that are no longer on demand. So that's the first major change that's coming to the electrical grid. And the second major change that's happening is that, in tandem with this, more and more of these endpoints are being monitored and they're being attached with communications. So more and more we can actually monitor what's happening here and control it remotely and hope to synchronize these things by solving some form of global optimization problem. So with this in mind, this is going to be kind of the outline of my talk, or at least some of the first half of my talk. Well, first maybe 2/3 of my talk. I'm going to start by talking about 3 applications we've worked on in the context of these smart grid systems. And these will all be at a fairly high level. I'm happy to talk about these in any more detail, but I want to cover kind of a broad spectrum of ideas here, because traditionally the thought is that power and electricity are kind of a physical thing, right? It's about building generators or building maybe new materials, or maybe enacting, on the flip side, enacting policies that encourage people to use more of a certain type of energy. And I think that there's also becoming a third pillar to this, which is information and how we can use control systems and automated intelligence to better control these things and better coordinate the grid as a whole. So in the first part, I'll talk about optimization applications in the smart grid. And as Pascal was saying, I come from an optimization and machine learning background. So most optimization here, though we do some integer programming, most of it here is actually continuous optimization. So it's a little bit of a shift, but hopefully it'll still be interesting nonetheless to everyone here. And the second half, if I have time, I'll talk kind of then more broadly, continuing this theme of optimization, I'll talk more broadly about some work we're doing in general purpose solvers, in this case for convex optimization, which I'll discuss what that means, or sort of what our contributions there in a second. But I think that this community actually has been excellent at sort of understanding the value in public solvers and abstracting away the solver from the problem specification. And I think actually there's a lot to learn from this work in the convex optimization community as well. Okay, so let me just jump right in and start talking about optimization in the smart grid. As I said, I'm going to cover 3 topics here in some detail, but also at a fairly high level here. Going to first talk about sparse wide area frequency control, then industrial demand side management for ancillary services, and then talk about energy disaggregation. So jumping right in, this first bit here is actually now seen to the conventional side of generation, but it's doing so in a way that hopefully is able to much more quickly respond to the fluctuations in this power supply that is induced by the presence of renewables and the growing penetration of renewables. So let's jump right in to primary frequency control. So I don't want to cover this in too much detail here because the details aren't too relevant, but the way that power systems, the generators are typically described, or a way they're described in a very high level view, is that each generator has 2 state variables. There is the voltage angle, which is, I'm using theta to denote here, and the frequency, which I'm using omega to denote. So the voltage angle, essentially, if you have a power grid where there's some amount of inductance on the lines, the lines are not perfectly lossless for both real and reactive power, then 2 generators spinning on this grid that are connected to each other will actually be slightly out of phase. They won't be spinning at the same, with the exact same angle. It's just a fact of the lines themselves and the inductance in these lines. And one way to quantify them, the state of a power system, is how far apart these angles are. So typically, maybe one of these is referenced to 0, but you can think of the state as being both these 2 power angles, theta 1 and theta 2 for each generator. And those can be a little out of phase, but if they start getting too out of phase, then you have bad things happen. I mean, these things start, they have voltage collapse, and these things start breaking, and you have outages. So you don't want to be too far apart. And so in some sense, the real issue here is the frequencies. So the frequencies are how much these angles are going to change to become out of phase with each other, because they both want to follow a reference frequency. Here it's 50 hertz, in the US it's 60 hertz. And if those frequencies get out of phase, get not out of phase, but if they differ too much, then you're almost certainly going to have collapse. So you really want to keep those two things in tightly controlled and tightly together. And if you write down the dynamical systems of the dynamical equations of this, here I definitely don't want to focus on this too much, but there's some set of differential equations that govern this system, where the state here is the time derivative of the angles is just how much each generator differs from the reference frequency. That's just the derivative of the power angle there. And the second equation governs how the frequency changes. So it depends on U, which is our control input. That's actually the power injection at each generator. It also depends on this is just some electrical equations here, but we won't worry about those. Electrical equations that depend on the actual angles. They come from, in this case, what are called the DC power flow approximation, for those that might know about this, but not too important. This captures the dynamics of the power system, relative to generators at least. And then this one captures the dynamics of the power system relative to the load. So this is the PL here is the load on the system. And so if either the load suddenly changes or something happens with the actual other generators and their power angle, there's a step change in the difference of the derivative of this angular velocity, and so you're going to start having things slowing down or speeding up. So we need to control the system such that these quantities, omega, are regulated at their desired frequency. And we're going to use to do this, we're going to use a linear control law, where here K is some gain matrix, X is the vector of all the states, and then U is then the power outputs for each generator. So really the only important point I want to highlight here is that the structure of this matrix is very important, right? Because if K has entries here, so they're on the diagonals here, the block diagonals, those are what's called local control, right? Because those saying I'm going to specify P1, that's the power I'm going to inject in the first generator, as a function of quantities I can observe at that generator, right? So it's as a function of theta and omega 1. Theta 1 and omega 1. Right? So if I only have entries here and here, then everything in the power system can be done locally. Right? I only need to look at my local variables to determine how to control the system. On the other hand, if I want to have off-diagonal terms, this is called wide area control, because we need now to actually have some sort of communication between these two plants in order for this one to sort of say what's happening at the other generators, right? These have to be quite fast, this communication too, because this is real-time control, and you want to be able to use fairly fast response or very fast information from the other generator, perhaps, to know how to control your own system. So this is really the upshot of all of this. These don't really matter, these equations here. This is the upshot, this difference between wide area control and local control for these plants. And we're not going to worry too much about delay, but we are going to worry about how much wide area control you want, because we're going to assume that if you have these terms here, you're going to go ahead and invest in a fairly expensive communication line, such as you actually can control these things. All right, so let's talk about sparse control then. The idea here is that if you think about not just two generators, but now a very big generator system, you would like it to be the case that you had very few off-diagonal links, right? That would correspond to very few, if this matrix was dense for a 50-generator system, that means you'd need to have a network where all were able to communicate to each other very, very fast. And this happens at a very fast frequency. This happens at the sub-second level. So you need very, very fast and very reliable communications then amongst a lot of different generators. What we want to do instead is still exploit some degree of wide area control. As I'll show in a second, there are actually cases in the power grid where you kind of need communication here to maintain stability without having voltage collapse. But we want to minimize the amount of control we actually have between these, or communication we need between these two different points. So this leads us to a topic called sparse control, right? We want a sparse control law where we minimize the number of off-diagonal elements of this gain matrix for controlling the linear system. Or not, I guess it's linear in that case, but for controlling the system. Now the problem here is that if you look at almost any control objective, and these control objectives are things like the limit of the expected cost, the continuous time expected cost over time, expected quadratic cost over time. All these things, they're all very nice because they're actually, you can formulate them in convex ways. You can solve them exactly using methods like LQR or H-infinity control. All these things become non-convex and hard to solve if you impose a sparsity structure on the gain matrix. So that's sort of too bad. In fact, it can be sometimes even hard to establish stability or instability of a system. I mean, stability you can prove easily if you just show something is stable, but it's hard to even know this is going to exist for sure with a sparse control law. So there are lots of challenges here. And the technique we take, though, which is actually also, I have the next slide. This is following, building on some work by Lin et al. In 2013. The technique we take here is to kind of ignore the fact that this problem is technically a very hard one. I think this is a common theme in this community, right? You just sort of ignore the fact that problems are NP hard and they're too hard to actually solve, and you go ahead and solve them anyway. And we're going to do that here, but it's actually even easier here because this objective, although it is can be hard to compute because it may actually be infinite for a lot of initial control matrices. It's also a smooth objective. Once you find any stabilizing controller, it's a smooth term. And it is non-convex. It's not convex in the gains themselves. But it's a smooth term. And so we can still use continuous optimization techniques to actually minimize this term here. And we're going to additionally constrain k to be sparse using an L1 regularization term on k. Right? So this is actually, this is sort of the standard thing everyone in every field now, statistics and machine learning do. But this term is actually hard to compute. So it's actually kind of nasty to compute this term here. As you can see, it's a big limit. You can compute it with a Lyapunov equation. So it is feasible to compute, even though it's an infinite integral here. But it's nasty to compute. You have to first solve a Lyapunov equation, then plug it in to compute this term here. And so, in fact, our main contribution really is on, in this method here, is on ways of quickly solving this optimization problem with this nasty objective term here. And again, I don't want to get too into the details here. If anyone's very curious, I'm happy to talk in more detail after the break. The idea is that we do things, so the idea is we're using what's called a Newton coordinate descent method. This is a Newton method where you regularize the Newton step itself with an L1 penalty, and then in that Newton step, you solve that Newton step itself, the regularized Newton step, using a coordinate descent approach. If that isn't, I'll show some results about how fast it is in a second. That's really the take-home message here, that it can be really fast. But internally, that's what's going on. And really what's happening is that doing that in kind of a naive way, even doing a Newton coordinate descent method in a naive way, with this objective defined implicitly by a Lyapunov function, is normally very, very hard to do. It would be about order n cubed, where n is the number of generators in the system. And that would just not be very feasible at all to do. And so what we do through a sequence of stages here is we reduce this to an order n per iteration algorithm by doing a lot of work with caching this Lyapunov function, by solving it explicitly in terms of eigenvalue decomposition and things like this. Again, I'm happy to chat about that afterwards. I don't think that is the sort of the math part of all this, but it's from a high level. I'm happy to breeze over that. But instead I'll just go straight to the results and how it performs, because what matters, of course, in practice is how well this can actually build controllers that have these desired sparsity properties. So we're going to use here a simulated domain, but a realistic one. This is a 48 machine, 140 bus system. So there's 48 generators that are a pretty good mapping to some generators in the Northeast. I mean, they are from the Northeast. They've changed a little bit since this was created, but it's still a reasonable system. And 24 of these machines are equipped with exciters and turbine governors, so they can actually control themselves sort of very, very accurately in order to inject more power into the system or take out power. Well, take out power just by basically injecting less power than their nominal amount. So we solved the system with our algorithm. And there are a couple things I want to highlight. The first is that this is the resulting gain matrix you get out of the system. So there are actually a lot of states at each generator, more than just two, because we also modeled the internal state of these exciters and governors. But the basic idea is there's more or less two states: the frequency at each generator and the power angle, and you can inject power then at these different states. And the amount of power you inject is governed by this matrix here. And you enforce sparsity of this thing. What you do see is that there's a much sparser structure in terms of the communication necessary between generators. And what this means is that we can use much reduced computation between the generators to actually still have some amount of joint control over these things. And I'll show the effect of that in a second. While not requiring sort of one-to-many communication or many-to-many communication for every single generator in our system. The next thing that I want to discuss is just how is the speed, I guess, of our, this is the result learning controller. I should also say we sort of pick lambda here. This is the regularization parameter, the trade-off between the cost function and the sparsity. We pick that through cross-validation. So we look at a few examples and say what's a good sparsity pattern that trades off communication with the control objective. But this is sort of the control, the final gain matrix we picked. And the nice thing, though, is this figure. So this shows the convergence of a bunch of different methods on the same problem. So in terms of actually solving this optimization problem, the common technique here, and in fact the technique that was used in past work, are first order methods like iterative soft thresholding, the fast iterative soft thresholding, and ADMM. But compared to these things, our method, I mean, it does much, much better in terms of time. These things will never actually converge. They'll basically just asymptote at a pretty high error, and not that much sparsity too. Whereas our method can find, it's a local solution, so we can't quite say it's the exact solution because this is a non-convex problem, but it certainly seems, if you initialize it at many points, it converges to the same spot. So it seems like this is more or less the best thing we can find, and it converges there on the order of, we can find a controller in something like the order of 20 or 40 seconds or so, whereas the others will never finish after hours. So finally, let's look at how this actually works. What I'm showing now is the response of frequencies over time that are caused by some step change in the system. So we basically imagine some big step change in the power consumption, or maybe a generator actually that can also be synthesized by a generator going offline at some point. And if you do local control only, this version actually is maybe it is stable still here, this case, but it can go unstable too. But essentially what happens is that these controllers, because they're only looking at their local variables to determine what to do, they're kind of doing independent PID control in some sense, or just PD control. They don't operate in concert, and they kind of fluctuate wildly. And so the actual frequencies here, they do eventually converge, or maybe they will eventually after a very long time. But they don't converge very quickly. And this is in comparison to the same perturbation caused by the same kind of outages with wide area control applied, with the sparse wide area control applied. These things are able to interact, and much more quickly they can stabilize the system at the frequency that you want. And you would I mean, this, when you have deviations this big, that actually can be quite bad for the power system. So much better to try to stabilize these things and get rid of them quickly. So that's the first thing that I want to discuss. Any questions about this? Yeah.
Yes. So you're trying to minimize the amount of communication. So
Yeah.
just like work with fault tolerance. Do you fall back to the local method if something goes wrong?
Yeah. So the question was, how does the communication, minimized communication, work in terms of fault tolerance? So we don't have that here. We're not simulating fault tolerance here. I should clarify. But Yes, the thing that you do is if certain links, the nice thing about these control laws is they actually do degrade somewhat gracefully because you actually don't regularize the local gains, and so the size of the gains in the off-diagonal entries are typically a little bit smaller than the diagonal entries, and so you can actually use that same gain matrix and ignore the off-diagonal ones and still have a stable system. It's not a good, it's this one. It's not a good stable system, but it's still stable. And what that means is it actually works very well in practice. It's just if a link goes down, you either just use a zero term for that state or you use some nominal term for that state, and things work pretty well. In practice, again, a lot of these things are kind of in practice because we don't have a lot of guarantees about sparse control in general, but in practice these things degrade very nicely and they kind of work well in that context. All right, great. Let me actually write it. I may not actually get to this too much. Well, we'll see if I have time for this in the end, but that's okay. I'm happy to get through the first three things. So let me talk about now a similar problem, but kind of from the reverse side. And this is a problem of industrial demand-side management for ancillary services. There's a lot of words there, but it's actually a very simple idea. The idea is typically, or at least in the past work, we talked about controlling the frequency of the system using generators, right? So and that's sort of traditionally how it's been done. So generators are the ones to pay for the fact that we're introducing all this fluctuation into the grid with renewables. But there's no reason why generators are special in this regard. You could just as easily do something similar on the load side, right? Where instead of injecting more power or injecting less power, you're just curtailing load or using more load, actually. And so if you can do that at the same rates as you can do the frequency control, then it's kind of just as good to try to change your load as it is to change your generation. So this brings us to something called frequency regulation services. It's not quite a market because there isn't a real market clearing process here because it has to operate much faster than traditional energy markets. But the idea here is that each participant in this service, not market, provides some capacity, which I'll call R megawatts. And then every 2 seconds, so the frequency here is a 2-second update, the system operator will broadcast some global signal to everyone. So now we are assuming that you have at least some communication that is somewhat reliable. Because actually, that 2 seconds is even quite a bit slower than how we reacted before. This is why this is called secondary frequency regulation, whereas the first one is primary frequency regulation. But every 2 seconds, they specify some signal, which actually maybe using bad notation, I'll call omega T2 here. It's essentially a signal that is dimensionless, but it varies between 0 and 1. Saying if the signal is -1, I need to consume, I always forget the direction it is. I think it's this direction, but if it's negative, it doesn't matter which direction it is actually. If it's -1, that means I need to consume an extra R megawatts. This is power, so we're talking about instantaneous consumption of power. And if it's +1, I need to consume, I need to produce R megawatts or consume less. It's not really production, so I just need to consume R less megawatts than I would otherwise. And that has to happen very quickly. Because the signal changes every 2 seconds. On average, it is balanced. So on the long scale, over the day or so, it will be balanced. But even for hours at a time, it can actually fluctuate up or down. And so when you see the signal, each participant has to increase or decrease their power by R, the capacity, times this signal quantity. And as I said, it's balanced, but it swings very fast. So it's natural so traditionally, the participants in this market were generators, right? It's the generators that actually went to also, actually, in addition to their primary frequency control, they would also provide some amount of secondary frequency control in a slightly different mechanism. But as I said, there is the possibility for consumers to participate as well. And we're going to in particular consider industrial customers. It doesn't really make sense for at least a single residence to participate in this because you have to be able to change your consumption at a very granular level here. maybe an aggregated group of consumers, maybe. It's actually a very much an active research area. But we're going to take a little simpler process and talk about large industrial customers, which have plants that can serve the purpose of this regulatory, of providing this regulatory service. And in particular, we're going to focus on cement plants. Cement plants they're complex things, but one element of these plants is what are called crushers. These are literally just it's a good name. It's the things that crush the stone to make the stuff that they mix with water then to make cement. And the nice thing about these is these can be turned on and off relatively quickly. You don't want to turn them off every second or so, but if you turn them off a few times, turn it off and on a few times in an hour, that's okay. It isn't going to impact the life of these things too much. And the other nice thing is that usually a plant will actually be sized for larger than the capacity of cement it actually needs to produce, right? They'll have more crushers than they actually need to operate at a single time because they want to be sized for, whenever they get their biggest order, they want to be able to create it quickly. They don't want to run out of crushers, but that means they can have some of them off sometimes. Now, the obvious problem here is that, by turning the crushers on and off, we can start to think about providing some amount of regulatory services for the grid. But the obvious problem is that crushers need to be turned, they're discrete, right? They need to be turned on and off entirely. The examples we're going to use, which come from a plant, we're doing this in simulation still, though in conjunction with some industrial researchers that also want to look into this in the plant. But these crushers are 2 megawatt devices. They consume 2 megawatts or nothing. And so we can't easily have them consume anything less. If you have, say, 4 crushers, you can't consume anything other than 0, 2, 4, 6, or 8 megawatts. And so the basic idea is, I'm sure the one that everyone kind of immediately thinks of here, but that's what we're doing, is that we're combining these crushers for these large discrete changes with a battery, a much smaller battery than what you would need to provide services based entirely on that battery, but with a battery that can kind of make up the slack between these large step changes that the crushers implement. So here is the basic formulation. And we're going to solve this using a model predictive control setting where we're solving an integer program to plan for things every 2 seconds. And actually the main thing that I want to highlight in some sense, coming from outside of the CP community, is that I was very surprised. I mean, some integer programs are things that either work well or they don't work at all, it seems like. Shouldn't quite say that. They usually work for small problems. But here we're trying to solve something every 2 seconds. And that kind of frequency either sometimes works, sometimes doesn't work. But in this case, it actually works quite well. And we can solve these things. There aren't that many integer variables here. And we can solve them typically in about, I don't think it's ever taken more than 0.1 seconds to solve this receding horizon mixed integer program here. So our mixed integer program, I should say, is X is the number of crushers that are operating at each given time. So we're going to plan for some horizon ahead using, and we don't actually know the regulation signal in the horizon ahead, but we're going to use an autoregressive prediction of it. And I won't get into details there, but it's a simple autoregressive model that we use to forecast the signal. And we're going to plan it out for about the next minute and a half. So we're going to have a horizon of about 45 discrete time steps. Each one is 2 seconds long. In our oscillation here, Y is going to be the battery power. So Y is how much power you inject or pull out of the system. E is the energy level of the system. And our objective here has really 2 terms. The first is the baseline. So, actually, the first part of the first term is the baseline power plus the regulation signal. The baseline is a level that you need in order to actually meet your desired quota of cement production. And the power here is the P is the power that each crusher consumes times the X number of crushers on, plus or minus, in this case, Y, which is the power we've put into the battery. And we minimize an L1 norm here, meaning that we're typically going to have those be equal. You can actually have them be equal always if you want, but we allow for a little bit of slack here because sometimes you would rather balance another control objective, which is the smoothness of these turning on and off these crushers. So you don't want things to be turned off too much, right? You don't want to every 2 seconds say now I want three crushers on, now I want one on, now I want two on, etc. So you want to enforce a smoothness penalty as well here. And by varying gamma there, you can trade off between how well I fit my regulation and how smooth my control signal is. Then here, for example, this equation is battery dynamics. I'm showing the version here without losses, but we actually use a loss version just to keep it simple. The simplest version is the energy minus the power that you take out, and you can easily add losses to that as well. And then you have just your ranges of your allowed variables. And there's a few more constraints. For example, on total switches, we often have a constraint on the total number of switches you're allowed to have over the course of an hour, say. And so you actually keep a history of how many switches have happened yet in the past hour, and you forbid more than that number, that number plus the ones you make next happening in the time frame that you care about. There are also some terms that encourage this thing to return to the battery at least to return to a steady energy level or a middle energy level, which kind of acts as a surrogate value function here, because you actually you have a relatively short horizon that you're planning over. So a minute and a half here, whereas you want the thing to operate over, of course, days. So I'm going to show you just a few examples from a small simulated plan. This is work done in conjunction with ABB research. So there's a lot of, we have not yet fielded it in an operating plant, but we're hoping to at some point. But for now, we're working with simulated plants that have reasonably accurate kind of models of dynamics for the systems and reasonable models of sort of costs here involved. I actually don't have a slide on cost next, but if anyone's curious, I can talk about the costs that are involved as well in this. It does end up being economical to do if you don't need to produce too much. If you have some slack in your production quantities, it does end up being economical to do here. So I'm going to show here is just two simulated versions of this. And as I said, one of the take-homes for me was just sort of how quickly we were able to solve these problems. We can solve, this 45 time step. So there's 45 integer variables that can range from 0 to 4 at each time step. And we're able to solve it quite well. And so these are the kind of results you get out of this solver. So on the top here, we see the AGC command. That's the signal, what it's called, automatic gain control. The dotted line there shows the resulting plant power. That's the sum of the crusher power and the battery power injections. And we are tracking that very accurately. We have a slight bit of violation. You can actually, there's always a trade-off, right, between the number of switches you need for your power and the violation you have. So you can always hit this exactly if you want. But some violation here is actually okay. And you'd want to trade off a reasonable number of switches for that. And you can kind of see here what the cement power does. So this is the number of crushers that are on, and it jumps these discrete levels, plus then the storage power, which is kind of following together that plant power, but making up for the difference in allowable quantities here. And these two bounds here show the range of allowable power draw that you can do with the battery. And so what we're doing here, in some sense, is we're providing, for instance, 6 megawatts of regulation to the system, which is much more than you can actually get if you just think about using the battery, because you are using the power of these crushers to actually make up the difference, or to sort of account for the large changes, the large baseline changes you want, while using the battery to make up the slack in this case. And by varying gamma, you can trade off between the amount you violate that signal and the number of switch points you have in your signal. So if I raise gamma here, I get now a smoother signal for my cement plants. I don't switch them on and off quite as much. So I only have 12 switches, for example, in this hour. But I actually do right here violate the AGC signal a little bit at a time where it sort of very quickly ramps down in this one situation. So there's definitely these trade-offs involved. And as I said, the main take-home, I think, of this is that this sort of online MPC works quite well with integer programming, in this case at least. And it can work actually in some sense because in MPC, oftentimes you have an initial solution of a good initial solution, namely your previous time step solution can act as a good initial starting point for next solution, which provides you a nice upper bound in a lot of your branch and cut methods. So you actually are able to pretty quickly partition most of the space and find a good solution there. All right, so the third thing I'll talk about is switching now to still on the consumer side, but now it's going to residential and industrial. Yeah, sorry, questions. I forgot to ask, yes.
Regarding the industrial demand side, the MPC horizon, how long is it? And,
Yeah.
And do you assume that you know the grid information for the full horizon, so you have a clairvoyant approach?
Right. So the question was, how long is the MPC horizon, and do you assume clairvoyance? The MPC horizon is 1.5 minutes, and we do not assume clairvoyance, no. What we do for predictions, so the only signal that really matters in terms of the predictions is this regulation signal, what that signal will be going forward. Because for regulation, you just need to follow that signal. That signal encapsulates the imbalance between supply and demand, and so that's the signal that's important. What we do for that signal is we develop and I didn't include this just for time, but maybe I should have now. But what we do is we build a simple autoregressive model on that signal, and that works quite a bit better than either assuming at some baseline or assuming like a persistence model for this signal. The autoregressive model works better than both of these two things. That being said, this signal is only predictable within a horizon of about 1.5 minutes. After that, it is a random walk signal, so you can't really do much. So what we do is we actually use 1.5 minutes of this prediction. So it's fully autoregressive, so it just is dependent on the past versions of the signal. Sorry, the past behavior of the signal. We use that prediction in lieu of the actual future regulatory signal, because otherwise it wouldn't be fair, right? Otherwise we'd assume we knew what the signal was, so it wouldn't be very fair. And that's why you sometimes have violations too. Is that sometimes the actual signal evolves very differently from how you predict it's going to happen. But the nice thing about MPC is that you have this recourse, right? That even when your predictions are really bad, sometimes it works really well in practice. And so our predictions are not great. They're okay, but it still works quite well.
And actually, I have also another
Yeah.
comment on the next slide. I had a similar discussion both this morning and yesterday with some of you. So the battery looks like an NMC battery from the power to energy ratio, and this battery aged not so well.
Yeah. So yeah.
Probably if you want to optimize the revenue
Yeah.
for the customer, you want to also have some sort of aging aspect in the model.
Yeah, so it's probably better. What's actually probably better here is actually have two stages. So you have like a sodium ion battery that's big. It sort of doesn't degrade. Is that the one? That's the saltwater batteries, right? You have one of these things, and actually you also use a fast response battery in addition to a slower battery. So you actually have sort of two tiers of fast response if you want to do this sort of really well. But yes, this battery, getting a long-term fast response battery with that capacity is not cheap. But for different sizings, you actually still can make. It does actually make economic sense for a plant to do this, just given how much money they can get off the regulatory market. It's about $10 per megawatt is the price of regulation in electrical in the U.S. at least, which actually, considering the powers that a plant like this makes, you actually can do a pretty good job with that.
But 1 megawatt hour battery is roughly 1 million.
Yeah. So the thing is these.
Dies after 2 or 3 years, you're not very happy.
Sure, but these plants also produce a lot of cement too, and so these crushers are big things, and so it doesn't. Yes, you do need to size the batteries properly, but you actually can make the economics work. At least again with our talking with our industrial partners, it seems like you can make them work, and maybe going forward you can make them work better. And so but yes, this is certainly an important point to consider. And you do in practice want to combine two different types of batteries to allow for one that degrades more quickly, that doesn't have to provide the whole 1 megawatt hour then, and one that degrades a little bit better, that can provide some of the energy while maybe having less power. Yeah. There's another question back there. Yeah.
Yeah, it was also about the battery, but I think it's a slightly different question about the battery that in your previous slide.
Yeah, so I'm showing the simplified one. To be clear, we do use a loss in our actual, but there is a loss in our actual model. I'm showing just this for for simplicity, yeah.
Non-linear.
No, so we do assume a linear response here. So we do assume linear, a linear inefficiency of the battery. Yes, you include a nonlinear one too, but the nice thing here is it is a linear system of equations, and so it is a mixed interlinear program here. So I would tend to just approximate it, even if it's actually nonlinear. That's how I would tend to do it. But yes, they are actually nonlinear, absolutely, yeah. Okay, so I think I might only get to this next. I might not get to this last one, which is fine. If anyone wants to know about, I'll highlight it just very quickly there, what we do at the end. But I'll talk next about disaggregation. So this is something that I've worked on for a while. And the problem in disaggregation is actually a very simple one. Now we're moving to we're still staying on the consumption side, but we're moving from industry to maybe the home or maybe a commercial area. And the idea of disaggregation is that we want to take something like an aggregate whole home power signal, or actually it doesn't have to be power necessarily. People are also doing this with things like water now and a lot of other types of signals. And we want to separate it out into its constituent parts. So take this signal and say, well, this part here is a washer and dryer. It's actually a dryer. This part here is a kitchen outlet, which is in this case a coffee maker. There's some electronics that are providing a baseline, and there's a microwave that turns on here at this point in the power signal. This also can be thought of as a single channel source separation problem. You only observe a single aggregate signal, and you have to separate out what's going on behind the scenes from that. And I used to motivate this in terms of consumer behavior. So consumers, when they see these things, may be more apt to change their behavior and understand their power consumption better and then change what they do. Spending a year in industry actually kind of made me cynical in regard to that, about how much customers really care about their power. But I still think it's actually hugely valuable for the same reason that we want to do things like frequency regulation. Namely, if you know what certain signals are, you can do a better job of predicting how they're going to evolve in the future. And you can actually build better predictive models of how well these things actually will operate going forward. And you can do things like quantify, without controlling it yet, you can quantify how much response there could be from homes, even if you don't go ahead and you aren't actuating it right now. So I think there's a lot of actually use cases for this, separate from just the standard one of trying to inform customers, which is a great thing, but I'm not convinced that'll ever get us super far. But I should say there are plenty of companies also still working on this, so it's still has not been proven one or the other. I'm just a little bit more cynical than I was 4 years ago. So the thing we use to model these systems is called a factorial hidden Markov model. So the idea is you have each each device in your home is modeled as a hidden Markov model. So you have some hidden state that quantifies kind of what state it's in. Each of these has an energy level. And then what you observe is not each one individually, but you observe the sum of all of these things. This is our model here. And then we assume you observe the sum of each one plus some Gaussian noise thing, where here x is going to correspond to the discrete state that each device is in, and y is a real valued output that depends on the mean emissions for each state here, plus some Gaussian noise. And this is a very old model now. Machine learning is 20 years old, but it's called the factorial hidden Markov model. Now, the inference task in a factorial hidden Markov model is just the following, which is exactly what we want to do, right? It says, given an observed output, we want to find the values of the hidden states. That is, we want to find what state each device is in order to know how much power each one is likely consuming. Once we know their discrete states, it's easy to estimate their actual power consumption. That's just a linear system. And so the standard technique for solving this is something called structured variational mean field, or the standard technique was something called structured variational mean field. And the idea here is that you hold all but one of these chains fixed. You assume you know the values for it, and you run inference in a hidden Markov model over the held out chain, and you just repeat this process for each one in turn. and this works okay. I'll show you in a second. Actually, doesn't work that well. But the idea is this is sort of a greedy local search, right? Because you have to assume some potential value. You then estimate your one given the others, but that can easily get you stuck in local optima. And as we'll see here in a second, it actually makes very bad decisions sometimes. And it's very badly suited to domains with lots of different HMMs together, where each one has a lot of different states. So our method for addressing this really looks at two different things. On the one hand, the first thing we do is kind of actually an obvious idea also. But the idea is instead of just looking at the absolute signal, I mean, everyone would do this, right? If you see this plot here, you wouldn't just look at the absolute power level right in this sliver here to determine what's going on. You would look at step changes, right? That tells you what's actually happening. It tells you when things are changing. And so what we do is instead of just looking at the total power, we look at step changes in power, which end up being differences in these quantities between two successive time steps. And in particular, if states change only one at a time, which we'll get to in a second, that's an important characteristic there, an assumption that we do make, or that we do use in our approximate solution, rather. If that does happen, then we would imagine that these different signals are very important because they exactly quantify some state's change in power. And we'll see in a second how we make that a little bit more formal. The second thing that we do is we develop what we call a robust HMM, which includes a component here which doesn't have any model at all. We model it rather with some unknown quantity z, some power level, where we put an L1, essentially an L1 difference prior on the change between successive time steps. So this power can take on any form we want, but we penalize changes. What that means is when we see a step change, if we can explain it with one of our models, we typically do, because otherwise we'll pay some cost relative to what the step change actually is in our robust component model. But this is very nice because if we don't have a model for every device in the home, this kind of picks up the slack and says, I don't know what that change is. I can't explain that change. Let me use this robust component to capture that signal I saw. And this actually can be viewed as what's called a total variation penalty, a difference in L1 signals, or it's a 1D total variation, also called the fused lasso in a different context, but there's lots of names for it. And it favors, it's an unknown power, but it favors piecewise constant. So it's applying essentially an L1 penalty or an exponential penalty, a Laplacian penalty, I guess, to the difference in signals, which corresponds to sparsity in this difference usually. And that nicely kind of corresponds to piecewise constant signals. Okay, so now how do we solve this? I'm going to go through this sort of very, very quickly here. What we actually do is we consider both the additive model and the difference model jointly. And the thing about all these things, these are all mixed integer programs. The integer variables or binary integer variables are the states. The linear variables are these robust components here. And this just says that these are these sort of indicators of what state we're in, these Q variables here. Have to belong to what's called the local marginal polytope of this graph, the HMM graph, and they also have to be 0 or 1 valued. And now we play some tricks. And they aren't very interesting tricks, actually. We're actually not going to solve it as an integer program. In this case, we're actually just going to solve it. We're just going to solve a relaxation of it, which, if you relax it in the right way, works well enough. What we actually do is, first of all, the additive just the pure additive model, we're just going to drop the integer constraint entirely. That if you just do that, that will work horribly. That's like trying to solve a subset sum problem by solving it by eliminating the integer constraints here, which wouldn't work at all. But we actually do keep this around because it actually helps things a little bit when you add it back to their model. But for the other one, what we're going to do is we're actually going to transform it. This is also a mixed integer quadratic program at the beginning. But we're going to, this sort of the nice trick about this difference model is that we can play this trick of converting it to a mixed integer linear program by enforcing this constraint that only one device changes at a time. And the way this works, just sort of really high level, is that we have, when you look at the likelihood here is a Gaussian, so it has a quadratic term in it. If you look at the individual terms here, what you'll see is that, and here I guess I shouldn't use this notation here. I'm using x now as the variable instead of q as before. But if you assume that you have some quadratic term, if we know that only one of these terms, so these xi's, are actually non-zero, that's how we encode it in a way that enforces this one at a time constraint, then we actually can ignore everything but the diagonal entries of this quadratic form. And of course, because these are binary valued, we just make this a linear term here. And that's how we convert it to a mixed integer linear program. This is not one of the mixed integer linear programs that's guaranteed to have an integral solution, but it usually does in practice. And so what we do basically is we just drop the integer constraint now, we have an LP, and we solve the sum of these two things, some way to sum of these two things. And the nice thing is that if you don't get an integer solution, the non-integrality you get is usually within a single variable, which I'm sort of okay with, right? It's sort of bad if you say that some power system is half of a dryer and half of a refrigerator, but to say that it's between two states in a dryer is not quite as bad. It can even be interpreted kind of probabilistically, and so we actually do this here, and this kind of works okay. So jumping ahead to performance, and I definitely won't have time for the last section. That's okay. I can just describe in 5 sentences what we're doing in the last section of this. But jumping to this, sort of how it works here. Here's the total power for a home. Here is the truth of what's going on, and here is the predictions that our algorithm makes. So it's getting it almost entirely correct. It's getting at least the dryer, the kitchen outlets, and the microwave correct. You notice there is some error here, and that's actually from the fact that if you look at the ground truth, actually some of this component that we don't really know about is the dryer itself. And so what's happening here is that this is actually a modeling issue. The dryers contain two things, where they contain a motor that spins constantly, and then a heating element that comes on and off. And actually, our model of the dryer only contained that heating element, not the motor that spun the whole time. So we captured that with our robust components. The unassigned here is just captured by that robust component. And for the most part, the things that we do assign are assigned quite well. And just to show some comparisons here, here's the true breakdown, here's our method, and then here are structured mean field and a purely event-based method, which both work much worse when you start having a lot of different devices that are coming on and off at the same time. And you can also look at this sort of over about 2 weeks in a few different homes here, and we typically do much better in terms of per circuit persistent recall than either previous approaches do before. Okay, so I'm going to pretty much, well actually, are there any questions about this? Take some. Maybe I can take these at my talk, because I have about 2 minutes left. So I'll finish up by just giving a very hand-wavy explanation about this last thing that I wanted to talk about, but you'll have to come and chat with me later if you want to talk about this. And that is, from a high level, what we want to do is not, all these techniques use optimization as kind of a core subroutine about how they solve things. And these are a mixture of convex and non-convex, but oftentimes we actually do solve problems with convex optimization. And in convex optimization, there exist some very nice solvers, both integer, both things like CPlex and these sort of standard solvers, but also modeling frameworks like CVXPy is one that I'm very fond of. For those that use another one well, I shouldn't say what other ones are, but check out CVXPy. I really like it a lot. Lets you write things almost exactly like they appear. Here's some CVXPy code. It looks almost exactly like the mathematical formulation. But the problem with these things is they're slow. They don't scale very well in practice. They actually, if you want to solve like a lasso problem, which we all love to solve in machine learning, if you have 10,000 variables, which for a lasso problem should take less than a second, they solve it very, very slowly. And the reason why is that they convert these problems to standard form. So whatever problem they have, these modeling frameworks take it in, and they convert it to standard form, something like a quadratic program, or actually even a second-order cone program in this case. And so no one would solve lasso that, or at least no machine learning, no machine learning person would ever solve lasso that way. I don't think anyone would solve lasso that way, or a statistician either would ever solve it that way. And so they're slow because interior point methods are slow. And so what we want to do is bring the power of more specialized solvers that people typically use in machine learning. These are things like proximal methods or ADMM. We want to bring those methods to the domain of general purpose solvers. So without going into too much detail, we actually show that, I'll just skip through these things. We show that actually using a combination of what are called proximal operators plus a new, well not new, but a sort of thing that has not been used very much in practice, which is called an epigraph projection. We show that we can actually take any problem that a language like CVX-Pi outputs and solve it using a conjunction of proximal operators, epigraph projections, which is it's actually just a projection onto the epigraph of some function. But we can solve these problems with a combination of these prox operators, epigraph projections, and solving linear systems. And when we do, you get things that are much, much faster. So this is a log scale of the speed that it takes to solve with CVX using a interior point method, an approximate solver, and then our solver, which I should say is also approximate. So I'm going to run into trouble here because these things don't actually satisfy the constraints. They do in the limit, but when you solve it, it doesn't actually satisfy constraints. It approximates everything, which is okay for a lot of machine learning problems because they're not actually constrained problems, right? They're actually just loss minimization problems. But whether or not you're okay with that depends on whether or not you're okay with a little bit of constraint violation. Maybe okay in the convex case, probably not okay in a lot of other cases. And we also actually are sometimes even competitive with specialized solvers that were developed just for this problem while keeping the entire language the same as what you use in a modeled language like CVX. And if you want to try it, it's actually also available at this epopt.io. Okay, so with that, oops, I even didn't have this here. With that, I want to end. Thank you very much. It's been great talking. Are there any questions now?
Hi, great talk. Just want to clarify about the level of empirical evaluation that you are doing on,
yes.
With each of the algorithms. So in the last example you said, well, when we tried on some houses and different, so can you elaborate? Because this is part of this community is doing a lot of empirical evaluation.
So actually, in disaggregation in particular, this is a topic near and dear to me because for a long time there was very, very bad evaluation in general on these algorithms, and there still is, to be honest. On this, we evaluate on a data set that we also developed. It's called the REDD data set, REDD, for the Reference Energy Disaggregation data set, which is actually, despite being fairly small, it's 6 houses over the course of a few weeks each. It's still kind of one of the standard data sets for this domain. People still use it. It's I think by far my most cited paper, a little workshop paper that I had that released this data set. So release data sets is always a good idea. You'll get a lot of citations by anyone that ever uses it. So the evaluation there was on this data set, but I definitely agree that this is not sufficient. It sort of indicates that it might be promising. It is not sufficient to say this is now going to be a fielded product we can deploy in 1,000 homes. I think that problem is still honestly kind of unsolved. For the level of data that we have here and the level of model specificity that we have here. You can do things like separate cooling loads and heating loads and large appliances because you can come up with default models for these things pretty easily. They kind of tend to work across homes. But oftentimes you have very specific devices in a house that are hard to generalize over different homes. And so here we do use, in this case, an unsupervised method for doing that, but then what you actually get out of this is you just get out labels saying this is device 1, device 2, device 3. You don't actually get out labels saying this is a refrigerator, this is XYZ. So I think that the first thing is we're using REDD, this data set, to evaluate it. That shows I think that's a good data set to use. People are using it. They're comparing against things, which I think is great. There actually is some comparison, which there wasn't for a very, very long time. Everyone would build their own data set and not share it. But there is still a long way to go. So companies like Constraint are actually ones that are now hosting public data sets that I think are very valuable. I think it's difficult to scale out to a very large data set with in a purely academic community. So Constraint is a nonprofit. They're part for-profit. I'm not quite sure what their current status is. But they are a group there that's trying to develop a similar data set that is publicly available, at least for academics. So I would encourage everyone that's interested to check that out as well. That's becoming kind of a new standard in this field. But there's certainly a lot of work to be done still on data.
In the disaggregation problem that you showed,
Yeah.
I think it looked like you need very high resolution
Yeah.
data, right? So from the smart meter in my house, I get maybe half an hour
Yeah,
resolution, something like that. Is there any?
That's a great question. So there's actually a whole range of things you can do with different frequencies. And you're absolutely right. This uses second level, 1 second level data, which actually a lot of smart meters can generate on a home area network. So if you buy a little device, you can actually get that high frequency directly into your home. And so you can do this kind of stuff. But you're absolutely right that back to the utility, they do not communicate this high frequency. We had a paper in AAAI in 2014, which was follow-on work to this, that uses hourly data to do the same thing. So we use hourly data for disaggregation. Now, the flip side of that is you cannot get anywhere near the level of granularity that you have here. So there we are talking about heating, cooling, large appliances, and then base load. It's basically 4 categories that you can separate out. Actually, no. For that one, we had a few more. We had refrigerators, and we had I can't remember the other one we got out to. But anyway, you're very limited in the set of devices you can do when you start talking about doing something like that. So what I would say is there is a whole spectrum of algorithms you can apply in different domains, but they are actually quite different, the algorithms we use in that domain, because now all of a sudden these sort of difference models aren't nearly as informative because you don't see those step changes. And that one at a time assumption is obviously wrong within an hour. More than one thing changes at a time. So there are different algorithms. We've done work on these different sort of levels of granularity, but I think it is probably worth doing more work and seeing exactly where those breakpoints happen in terms of levels of granularity and allowable levels of performance in disaggregation.
On the same part of the talk, I'm just wondering how good are these HMM models in the first place?
How good in what respect?
I mean, I guess it depends on what you choose to model, right? So one is choosing I guess you are choosing here some kind of HMM model.
Yeah.
But is that model a good model in the first place?
Well, I guess it depends on what you mean by good. It is good. I mean, so they aren't just single state. They're actually multi-state models that capture the different levels of power that a device can be in, like in a standby mode or other modes like that as well. And usually we have like 10 or 15 states per device. So they're reasonable models. Having said that, if you just sample generatively from these models, you don't get signals that really look like these things, right? If you just sample generatively. But the nice thing about HMMs is that oftentimes they work well even when the generative model is bad, right? So you don't actually always need that good of a generative process to still get good performance from them. So they're good in the sense that they capture the power levels. They're not necessarily good in the sense that they generatively look like the devices themselves. But I think it's actually less important in some ways because what really matters is their performance when you separate things out. And I don't think the HMM models are necessarily the biggest problem here. I think that it's actually the inference problem and coming up with those models in the first place. If you have the models, I don't think that's the problem. They're not expressive enough. I think finding the models and then doing the inference are the harder problems. Some questions?
So do you know if there has been any work on using the output of the disaggregation models to learn models of behavior of people with respect to how they use certain appliances, because that could be pretty useful.
Yeah, so there has been some work that I've seen on that. We have not directly done that. As I said, I'm actually moving more towards that as a motivation, or at least models of models of homes from an electrical standpoint are actually, I think, almost a better use of a lot of these models than maybe just informing customers alone. I have seen some work on, yes, trying to at least, if not infer things about, and I can't remember the authors of this paper, but it was sort of about jointly inferring kind of human behavior and disaggregation, and using each one to feed back to the other, right? Because if you know the person's at home, you can have different models as well. So I forget, it was at one of the CompSUS tracks some year. So I believe there's been some work in that, but I'm blanking on what it actually was now. I have not done that work though, yeah, or too much of it.
More questions?
Holding everyone coffee so we can, by all means, come talk to me at the coffee break.
Okay, so thank you very much for a very nice talk.
Thank you.